Okay, so the next speaker is Brijesh Kumar. And he's going to talk about understanding spin-1 Kagome antiferromagnets through the Hida model.
Why is it not displaying mirror? Is it okay? Okay, good morning, friends, and thank you, organizers, for inviting me to speak at this meeting. In the next 40 minutes or so, I'm going to speak about a recent calculation of mine with my student Pratyay Ghosh, who is sitting in the audience. These are the two primary references in which those calculations were published, and they are to do with the spin-1 Kagome antiferromagnetic problem. Kagome lattice, which is the object of our discussion in my talk, in particular the Heisenberg antiferromagnetic model on this lattice, is an interesting frustrated problem, and we all know it because the motif that makes it, the triangles, antiferromagnetically interacting spin triangles, are geometrically frustrated, which makes it one of the most highly frustrated spin models and also a complex one to study and understand. Of course, it appeared first through a star triangle relation in StatMech in the study of the Ising model on a decorated honeycomb, which in some way turns into what is our Kagome lattice. For students, it was named so by a Japanese gentleman, Koji Husimi, and you can read this paper for a nice history of this Kagome lattice, the lattice holes or the basket with holes. In fact, in this paper, if you read it carefully, there is a conclusion drawn by Shuzi, who says that, and remember, he's studying frustrated, in fact, in those days, frustration, the term was not coined yet. In human life, people always knew frustration, but not in physics. And so people didn't quite know what to expect from such a model problem. But what he did see, that what he says in the antiferromagnetic case, there is no phase change. What he means is that there is no phase transition to an ordered phase. So the peculiarities of the frustrated nature of this lattice were already showing up, although people did not quite appreciate in what way the geometry of the lattice is playing such a critical role in determining the physical property of a problem. Of course, the reason why we study them now is because there are realizations of Kagome antiferromagnets in real materials. This is, of course, the most famous one. I don't intend to review the subject, but just to sort of flash through some key points. So this is a mineral Herbert-Smithite, which is supposed to be a nearly perfect realization of quantum spin half, a Kagome Heisenberg antiferromagnet. There is no magnetic order down to whatever low temperatures experimentalists have gone. From a theorist point of view, it's a really challenging model to keep oneself busy for years to come, and that has been the case for the last few decades. Spin half case in particular has been the most extensively studied problem and also very heatedly debated, and people still have camps and want to stick to that unless they have strong reasons to convert. In fact, one of the earliest serious computation on spin half Kagome antiferromagnet was done by a French group, and the interesting aspect of this calculation is that there are, even on a finite cluster, so this is the difference between triangular lattice antiferromagnet and Kagome lattice antiferromagnet. In case of Kagome antiferromagnet, they find a huge sort of low-lying singlet or resonating, valence bond sector or singlet sector. Frederick Miller, in fact, made an interesting computation or estimate of the number or the size of this sector, and he says it's exponentially large in system size. It's certainly a case for quantum spin liquid, realizing quantum spin liquid states. But from 1997 to 2018, and this is, as I said, by no means a review of this subject, but you can see people have different viewpoints and serious ones based on serious computations, and one is not quite sure what is the real ground state of quantum Kagome antiferromagnetic model. But I'm not interested in spin half. So in this talk, we are going to talk about spin-1 Kagome, which in fact, from the materials point of view, is in fact, in some sense, the interest predates even spin half case. There was this organic salt whose name I do not intend to pronounce, but it is some complicated organic salt, which at the end of the day, experimentalists characterized and found to be a layered kind of material made of effective spin half moments. And the susceptibility is basically typical of a spin-gapped system with activated behavior at low temperatures and going to zero, basically. This is one of the earliest, in fact, motivation for studying spin-1 Kagome systems, but there are others more recently. And for instance, in sodium vanadium oxide, which is, of course, an organic material, you have three kinds of vanadium, and of which one of them forms Kagome layer, which is the one which is more interesting. And there is even a transition as a function of temperature from regular Kagome to a trimerized Kagome. But I think this system is a little more complicated than just the lattice geometry. So based on, motivated by this organic salt, Hida basically went on to do the first systematic studies on spin-1 Kagome problem. So as you can see, in fact, this is the model that Hida constructed, which is directly motivated by this structure that experimentalists suggest. So in a nutshell, you can think of it as antiferromagnetic hexagons. So these red bonded hexagons are the antiferromagnetically spin halves. But they are coupled ferromagnetically. So these blue links are the ferromagnetic couplings between these antiferromagnetic hexagons, which is in fact nothing but the effective physics of these organic salts. And so this is what you can write down as a minimal model, antiferromagnetic hexagons coupled ferromagnetically. So JF is negative, JA is positive. And as you can see in this material, the estimated values of these couplings are almost 8 times of each other. So ferromagnetic ones are stronger by 8 times than the antiferromagnetic ones. So you can think of these blue bonds or blue links as being very strong ferromagnetic bonds compared to the red ones. So in the limit, if you take, as a theorist, you consider the limiting case where the ferromagnetic bonds are very strong, the links are very strong, then it essentially turns into this is in fact, so although the underlying microscopic model is a model living on honeycomb lattice, but with mixed ferro and antiferromagnetic couplings, but the effective limiting model is a spin half quantum antiferromagnetic model. And this is what, in fact, we call as Hida model, just to sort of, because this is where it all started. Yeah, then Hida actually discussed not just that connection between Kagome physics and the organic salts, but he also then made a proposition for the ground state, that what could be the, remember the susceptibility curve and other measurements tend to suggest that this is a spin gap non-magnetic system, some kind of a quantum paramagnet. So what could be the likely ground state of this low temperature phase of this material? And so what he says, well, okay, you have these antiferromagnetic hexagons. So at the simplest level, I mean, this is just in my simple words. So you form basically, you locally satisfy the antiferromagnetic exchange on each hexagon by forming a singlet. So these are hexagonal singlets, the product of hexagonal singlets. But because the materials have JF as large, so you would like to basically symmetrize these spin half pairs sitting on the ferromagnetic links. So you form these hexagonal singlets, and then you symmetrize these blue links, the ferromagnetic links. By symmetrization of a pair of spin half, you mean you are basically making it a spin-1. And this is a procedure which is well known in quantum magnetism as AKLT type construction. Yeah, I mean, I don't have to go into the details of that. But basically what it means is if you have, let us say, a spin-1 chain, then you can think of each spin-1 as 2 spin halves. So this is spin-1. This is spin half. And then you make valence bonds like Hida is making the hexagonal singlets. And because in the end you have to generate the physics of spin-1, you symmetrize each pair of spin halves to make a spin-1. So this is why I'm saying it's an AKLT type state. In fact, the name HSS was, so AKLT called these kinds of states as valence bond solids, and what Hida called it hexagonal singlet solid, because it is analog of the valence bond solid, but for hexagons. Now, this candidate state is a non-magnetic state. It doesn't have any magnetic moment. It's a quantum paramagnet, and it breaks no symmetry. In fact, it breaks no spin symmetry, it breaks no lattice symmetry. It's a perfectly symmetric state as far as the symmetry. So this looked like, to begin with, a very nice candidate state to describe the physics of this material, and by extension, in this limiting sense, the physics of spin-1 Kagome Heisenberg antiferromagnet. However, this question has been revisited recently, and in fact, energetically better candidate for the ground state have been identified. In fact, in a span of few months, 2015-16, a number of papers appeared, including ours, where we all advocated in our own way through our different means, computational, analytical arguments, and so on, that actually the correct physical ground state for spin-1 Kagome Heisenberg antiferromagnet is not the non-symmetry breaking Hida state or Hida's hexagonal singlet solid state, but a spontaneously trimerized singlet state. Where, so this cartoon here tries to depict the following thing. So this is Kagome lattice, and on the vertices of, on each side there is a spin-1. Now, whether it forms these hexagonal singlets, no, that is what the people find. What they find that actually spins like to locally satisfy the exchange on triangle and form a triangular singlet. So if you think about this construction here, a triangle is again, so instead of forming an hexagonal singlet, what they are forming is a singlet on the triangle. In fact, this is, once we think of it, and once we find it doesn't look, in fact, unreasonable. It looks more reasonable than hexagonal singlet case. If you go back and recall the frustrated model physics starting from Majumdar-Ghosh chain. So Majumdar-Ghosh chain is a nearest and next nearest neighbor interacting spin chain. It's a quantum mechanical problem. Frustration doesn't allow magnetic order to set in. So what does quantum mechanics do? It helps the spins to find, if possible, a neat paired local singlet states, because it can't order, so therefore it locally tries to satisfy the interaction. That is a qualitative way of thinking about how spontaneous dimerization happens in spin half systems in these strongly frustrated situations. Here you have a similar situation. You have a strongly frustrated spin-1 problem, and the order is beyond the reach of spins, but can they locally satisfy interactions and gain a quantum mechanical, or arrive at a satisfactory quantum mechanical local state? And that local state for spin-1 triangles is possible. You can form a singlet. For spin half, for example, as I said, spin half has been strongly debated and not settled. If you do the same exercise for spin half, you can't form local singlet using 3 spin halves. So there is, even if you try to think of this trimerized physics, you still have a pseudo spin half sitting on the triangle, and then you still have the dynamics of that pseudo spin half on the entire lattice. So it's a much terrible, complicated problem. Whereas for spin-1, that possibility is available, qualitatively speaking, that locally in the frustrated situation, spins can form a singlet locally at the triangle level. And it turns out that this is what actually the spin-1 Kagome antiferromagnet is doing. So the way we view this problem, just a sort of brief outline of what we thought. So what we think of, the Kagome lattice is, of course, a network of triangles, so corner-sharing triangles. Now, we also added, just for generality, next neighbor interaction. So we think of this. Suppose there were no inter-triangle couplings, so the green and blues were all 0. Then you anyway have this, trimerized singlet state, which is a unique but trivial idealized ground state. Now you turn on these inter-triangle couplings, the green bonds, that makes it the Kagome lattice. For generality, you can also add second neighbor interactions, etc. It turns out that makes also some interesting contributions to the physics, but in the ordered case. So then what we do is we start from this given trimerized singlet state, and then turn on these intertriangle couplings and see at any point if this state becomes unstable, at least to the triplet fluctuations of this effective theory, or this singlet gap survives and the triangular singlet phase is a good phase. So basically what we do is rewrite this entire model in an effective bosonic theory made of these so-called placket operators, which are analogs of the bond operators that we are so familiar with in the dimerized antiferromagnetic problems. So what we do is we locally construct the Hilbert space in a restricted way because quintets, etc., are very high in energy. So just look at the unique singlet and the lowest lying triplet excitations and construct some effective bosonic theory. And the result of that theory is this phase diagram. So first focus on just this simple case, forget about these two phases. So J double prime 0 means there is no second neighbor coupling, and this point J prime 0 means the triangles were isolated. So of course they form a trimerized singlet state trivially. But then interesting point is as you turn on J prime and go all the way to this point, which is the usual, the Kagome point, the gap nowhere closes, the singlet gap is intact, and in fact the trimerized singlet order survives. So it's in fact, so what we say that at least within this simple-minded picture, there is no harm to the trimerized singlet state that we conceive of as a possible candidate state, and it survives all the way up to the uniform Kagome case. In fact, at this point, so all the while this is a given trimerized state, but at this point, the green and the red bonds, red triangles are basically same. So this is a spontaneous case. It could have been up triangles or it could have been down triangles. So in fact, trimerized singlet state is a good state, but people have done more sort of systematic numerical calculations using DMRG, ED, tensor networks, and also basically find what we have found in much simpler qualitative manner. In fact, just as an aside, what we also discovered in this model that, so conventionally, there are two ordered phases. When we introduce second neighbor coupling, one knows two ordered phases that are expected to occur in a Kagome antiferromagnet. One is the 120 degree root 3 by root 3 phase. So on each, let me in fact show the figures, which is well known and there is nothing new about it. But what we also find that the Q equal to 0 phase is actually unconventional. So what people know from semi-classical analysis, this angle should have been 120 degree exactly. But what we find that actually this angle is not 120 degree. This is slightly deviated from 120 degree, and this angle delta, this deviation angle delta depends on the degree of frustration, the ratio between J prime and J double prime. And in fact, let me show you that phase diagram. Only when J double prime and J prime are equal, delta is exactly 120 degree. In fact, we also computed structure factor for this phase if this fine distinction could be picked up by an experimental signal. And there are certain peaks in the extended Brillouin zone diagram of the structure factor, which are actually different from the other 4 points. We actually calculated the intensity ratios also. So basically the ratio of intensity of this peak and that peak is precisely the measure of this distortion delta. And in fact, we looked at the literature. If somebody had calculated something similar for spin 1 case, there was none, but certainly for spin half case, which is more extensively studied, people had calculated in the problem with second neighbor coupling. And interestingly, what people find in the spin half case, I'm talking about ordered phase right now, just this is a remark on ordered phase, is in fact, if you look at this figure, the symmetry of the spots intensity is very much like what we expect. So 2 of them being same, but the 4 of them being different and so on. My feeling is that the quantum paramagnetic phase for the 2 cases would of course depend on what spin quantum number you are looking at. But once the order sets in, the spin quantum number is no more important. What is important is the magnetic moment that has developed in each unit cell. And as soon as that develops, the physics is in fact going to be common for spin half and spin 1. So what people had been computing for spin half case, my feeling is in fact what we are finding systematically and predicting for spin 1 case. But it's just that people did not actually realize that that was the case. Next nearest neighbor. In this particular calculation, which I took from somewhere, this is, I think, Sherlock's group and so on. This is, so J and J prime are equal, that's a Kagome lattice. But in addition, there is a J2, the next neighbor coupling. Yes? No. So these two figures, for example, let me see, just 1 second. So J2 is same. In fact, the asymmetry in the peaks due to the aspect ratio of the cluster that one chooses reflects in the distortions of the peak shape itself. So I'm saying it has nothing to do with the intensity. I'm talking about intensity. So this distorted peak is same as this peak, except that the geometry has made it look elongated in some way. So I strongly believe, and I think people should relook at this in view of what we are saying. I'm saying the singlet physics or the quantum paramagnetic phase is different for spin 1, spin half, obviously. But once the magnetic moment sets in, the order sets in, there is a non-zero magnetic moment per unit cell. I mean, sorry, on each side. The ordering of magnetic moments is governed by the frustration present in the Kagome lattice. And that, I think, would be actually similar both for spin 1 and spin half. I haven't calculated the case, calculated it for spin half case, but certainly for spin 1 we know, and we make this strong prediction. But I'm saying there is, it's just a matter of, okay, I might be wrong, but then somebody has to go and relook it in the view of what I'm saying. I doubt it. Yeah, no, because I'm saying I'm making a qualitative observation. See, suppose I give you classical moments and I give you J2 interaction. I'm saying with some kind of fluctuation theory, you would, in fact, the reason why these two peaks are different is because in this particular phase, there are two nearly degenerate spin wave-like modes, at the Goldstone modes. And the delta actually in some very sensitive way depends on the ratio of the spin wave velocities. So it's just a matter of, you know, some exchange interactions and some moments and their Goldstone mode physics. So, yeah, so that I cannot comment because I am not an expert on some of those techniques. But all I'm saying is, I read those remarks carefully in their papers, and in fact, let me make you share another observation. So you see this line where they also say that the intensity, these data I think correspond to this 45-degree angle, where J2 equal to J1. And that is where they find perfect, the most confident perfect 120-degree order. And let me show you the phase diagram. Only when J2 equal to J, so in my notation J prime equal to J double prime is same as 45-degree angle there. It's only then you expect to have perfect 120-degree order. So I am actually quite hopeful that what they are computing for spin half in the ordered phase is reflecting of what we are saying in the ordered phase of spin 1 case. But here it was sort of, it turned out to be, I mean, it was easier to sort of do it, but I hope, yeah. No. I mean, okay, precise numbers I don't have. I'm just saying, look at, just make some qualitative visual guess for your argument. I'm saying there are 4 peaks versus 2 peaks, and they have a certain ratio, and that is the measure of distortion angle. So I'm saying now reverse it. If you see this difference, that means there is a distorted 120-degree order. And to me, these 2 peaks look very similar, whereas the other 4 peaks look different. So you might say precise values may be different. As I said, I'm not even commenting on the precise numerical detail. I'm saying qualitatively, this feature, it seems, is appearing is not a coincidence. But let me go ahead, because this, as I said, what the... Otherwise, the chairman will, stop me after 10, I mean, whatever, my time is running very fast. Sorry, Yasir. Yeah. So, in view of these findings for spin 1 case, that the original view of the ground state of spin 1 Kagome as proposed by Hida is not the correct one or not the most favorable one. Let us revisit. So these organic salts, what do they realize? I mean, do they really, remember, these are not still spin-1 Kagome. They are some honeycomb-like problem because JF is not truly infinite. So we have to worry about that question. So is the HSS state of Hida still valid for these class of materials, or this class of, I mean, this model, the Hida model as we call it? Or indeed, they show some kind of trimerized singlet state, as we now reasonably confidently understand for the spin-1 Kagome. In fact, my student did some survey of all the materials which fall in this category, and there are different ratios of JF by J that are available. And so, in fact, so it's very reasonable to, in fact, ask, how does the ground state of Hida model evolve as a function of JF by J, and where do they fall? Where do these materials fall in this evolution? So let us argue qualitatively the possible candidate states. So let us look at this weak coupling case when the hexagons are very weakly coupled. In that case, it is not unreasonable, again, starting from an ideal point when JF is 0, that these hexagons actually form a local singlet. So this cartoon here shows that each hexagon, these red lines are singlet states, and they are weakly coupled. Okay. But so this is a hexagonal singlet state, but still I would like to call it, I mean, it's different from the HSS of Hida, because remember, Hida was also doing symmetrization. So when you do the symmetrization of spin pair on the ferromagnetic bond, you are actually by default assuming strong coupling limit, but this is not strong coupling. So he is in some way thinking about hexagons as being given, and then which is in fact reasonable only in the weak coupling limit, but then you are not supposed to do symmetrization. So I'm calling it HS instead of HSS. Okay, so this is weakly coupled hexagonal singlets. In the strong coupling limit, we now know that it has to be trimerized singlet state for the Kagome case, but to redo the same, I mean, rewrite the same thing for the honeycomb lattice, the Hida lattice, it basically means that, so there are these, hexagons with staggered antiferro couplings, and which are similar to the triangles, up or down triangles, and you just pick any one of the triangle as forming this kind of triangular lattice, I mean, singlet state. So basically, this is your trimerized singlet. Now, what happens in between? What kind of state do you expect in between? A priori, it was not obvious, but then we just carefully thought about what is trimerized singlet state. In fact, from the Hida model's perspective, trimerized singlet state, I'm just zooming on to any one of these hexagons. The trimerized singlet state from the spin half Hida model point of view is nothing but a dimerized singlet, hexagonal singlet. I mean, what we are calling as trimerized singlet for spin 1 is essentially a dimerized hexagon for the Hida model. So in fact, what we think that, but remember, there is one difference between these two. These shaded, thick, figure here is basically just telling you symmetrization. There is no symmetrization here. So let us repeat. This is weakly coupled hexagonal singlets. This is spontaneously trimerized or trimerized singlet states, which means any of these up or down triangle units are picked up. And in between, you still have the dimerization persisting, but there is no compulsion on the two spins to be symmetrized. Right? You can think of it like this. Initially, the hexagons were uniformly forming singlet. Now the hexagons are showing spontaneously dimerized singlet, but still no compulsion on the spin halves to be forming a bound state, or if at all they are loosely bound, they are not behaving like a strongly bound spin 1 state. So let us see if it comes through meaningfully through some calculations. So first we just take these 3 candidate states and do triplon analysis, which means take these as reference states and then look at the low energy excitations and calculate their ground state and so on, and then compare. Obviously at JF very small, the red dashed line, which corresponds to the HS state, the hexagonal singlet is lowest in energy. But as we grow JF further, it is the dimerized hexagonal singlet, which is the blue dashed line, which comes down in energy, as expected. And this brown colored line is the trimerized singlet state. And you see that they don't cross, in fact, they merge, which is what that figure suggests. This says that, in fact, as you increase the coupling, all that you have to do is, dimerization is already there, all you have to do is form the spin pairs into spin-1 pairs. So the trimerized singlet state, viewing it from the Hida model perspective, is nothing but an adiabatically continued dimerized hexagonal singlet state. All that is happening is, initially these dimerized hexagons were not loosely coupled, now they are strongly coupled, but the physics is essentially same. In fact, these materials, if we put on this axis, even if these numbers are only approximate, you see that all these materials actually fall in the trimerized singlet phase, or in the honeycomb language, the dimerized hexagonal singlet phase. The degree of, in fact, you can even, see, you might wonder, all these states are non-magnetic, and from the susceptibility measurement, you can't make out the difference between these subtle differences between the trimerized singlet, hexagonal singlet, and so on. So what can you do? Again, we calculated static structure factor and try to sort of see how do they look. Well, just qualitative figure like figurative, not figurative, but figure, looking at just the figures. This is for the hexagonal singlet, this is for the dimerized case. Now, in some way, the intensities are readjusting. Overall, they look similar, but if you see the curvatures properly, if you go along this line or if you go along this line, the intensities have different behavior, in fact. And we precisely identify the cuts in a neutron measurement along which the intensities will critically differ. Everywhere else, they look similar, but only when you go along in the first Brillouin zone from this center of the zone to that center of the, zone boundary. And in the extended zone, you follow the same line parallel to that. You will see that the way in which, so this is for the HS, this is for the dimerized case, where the intensity peaks or the maximum minimum difference is more is completely reversed. So you will automatically have a feeling for whether the system is actually in the HS phase or in the DHS phase, depending upon how the neutron diffraction intensity varies along these two cuts. So that is one sort of simple, because otherwise there is no obvious way of distinguishing between all these non-magnetic singlet states. So here I'm not, so these dimerization or trimerization business, I'm not invoking them as a result of some lattice helping them to distort. No, not always. So for example, in 2 dimensions, in principle or in higher dimension, there is no compulsion that the lattice has to deform to form trimerized. That's right. So, but does it have to? So, okay, that's a subtle question. So, what one can do at the next level, maybe invoke some soft phonons and see if they also necessarily, But at this level, there are no phonons here. There is no lattice distortion here. Okay. So, I'm saying even if suppose, see, in 1D there are these strict theorems which say that dimerization happens simultaneously with the lattice being distorted. But in higher dimension, there is no such compulsion, I'm saying. If it happens, for example, people talk about so-called breathing Kagome, breathing pyrochlores, all that is basically physical, trimerization or quadrimerization and so on. So if that also happens, that's fine. I'm not against that, but I'm saying this is purely spin physics, not invoking the lattice physics. So then so this was the analysis based on the, yeah, I still have some time. So this was the analysis based on sort of some making some qualitative guess about what states you expect, and then doing some stability analysis and finding that it conforms to what we believe should have been the case. So now we do, we check this again by a slightly less unbiased, in fact, unbiased calculation. Unbiased, what I mean by that is, I'm not assuming a priori that there is a dimerization or not. It is the self-consistent calculation which will pick whether there is a dimerization or not. So we use Schwinger boson representation to describe the spins, and this is very standard. Then exchange operator in this language can be written as sum of some pairing operators A and some hopping kind of operator F. And then we apply a mean field approximation. So the mean field approximation is actually quite simple. The blue bonds, the ferromagnetic bond, we define some mean fields, which system will self-consistently find. For the antiferromagnetic bonds, we remember there is this up-like object and there is this down-like object. So we just assume A is to be alpha and phi to be different on this or that. Because if the system were to pick dimerization or trimerization spontaneously, they would be different. If the system chooses to stay uniform, then they will be same. But it is not we who are a priori fixing it. It is the self-consistent dynamics of the system that will determine whether A and A prime or, alpha and alpha prime and phi primes are equal or not equal. If they are not equal, that would mean dimerization. So the result of this calculation is basically two phase transitions that the system exhibits. So this is a calculation, this is a calculation of dimerization order parameter. So if you look at this, look at a single hexagon, all we are saying is we are computing such a quantity, OD, which is the difference of singlet weights on these 3 bonds and the other 3 bonds. If that difference happens to be 0, then the system is not dimerized. If that difference happens to be non-zero, then system is dimerized. So we are just looking at average singlet weight on the 3 different bonds, these 3 and the other 3 bonds on each hexagon. So this is sum over each antiferromagnetic hexagon. And what we find, at least within this approximate calculation, that for very small JF, so as soon as you turn on JF, so in the when JF is 0, of course, this is all uniform hexagon, but as soon as you turn on JF, not for very strong JF, it already tends to dimerize. So that is conclusion number 1. And this looks, so if this is your order parameter, it was 0 to begin with and non-zero and continuous. So it looks like a quantum phase transition, dimerization quantum phase transition, from one kind of singlet phase to another kind of singlet phase, which is the dimerized case. Then we calculate how the moment evolves, because remember all this qualitative discussion we were having, it talks about whether the moment has formed strongly or not, because that is the critical difference between this hexagonal singlet phase in the weak limit and the HSS, which is supposed to be strong coupling case, but with symmetrization, which is strong coupling physics. So let us calculate how does the moment forms. Now, interestingly, if you look, so the quantity that we calculated, this object, so average total spin per ferromagnetic bond, again within Schwinger boson mean field approach. You see, look at this expression. If the 2 spins were uncorrelated, the 2 spins on a ferromagnetic bond were uncorrelated, ideally suppose, then this term is simply 0. And you should get for spin half case 1.5, which is what you are getting. In fact, then, so now when you turn on JF, you would expect it should have probably continuously grown, but at least our calculation surprisingly shows that it nearly stays 1.5. It nearly stays 1.5, and only after some other critical, some value, JF of around 1.5, minus 1.5, it begins to grow, and eventually it tends to what we expect for spin 1. So this is another sort of continuous, so the moment is staying constant or as if it were 2 independent spin halves. So while the singlets have dimerized, the moments are still behaving as nearly uncorrelated. Uncorrelated is not the right word, but not forming a bound state. That is the correct word. And beyond a certain critical strength of ferromagnetic coupling, they start to form bound state. Initially, but the moment, of course, doesn't immediately become 1. It becomes 1 only when JF is sufficiently large. And this we call as moment formation transition. So basically, the physics of Hida model and that of spin-1 Kagome lattice, as motivated by these organic salts, is governed by these 2 phase transitions. So in the first stage, as soon as the antiferromagnetic hexagons get coupled, they tend to form dimerization. Now, you might say this may not be minus 0.3, it may be some other number that can be computed and should be computed by other different independent means. But there is a dimerization physics which is setting in right at the beginning for small JFs. But the moment formation doesn't necessarily happen at that point. So you may have these dimerized singlet, but one hexagon, the spins of one hexagon are not strongly bound to the spins of the other hexagon. So that is the moment formation. So initially they behave like nearly independent spin halves or unbound spin halves, but only when the critical coupling, the coupling is more than some value, they begin to form, behave as bound moments and not two spin halves. And with that, I basically summarize my talk. The spin half Hida model applicable to a family of spin-gapped organic salts exhibit two transitions in the spin-gapped singlet ground state with respect to JF by JA, the parameter in the model. It first undergoes spontaneous dimerization, and then it undergoes moment formation, by which we mean initially they behave like spin halves, and after that they behave like bound spin half moments. So you can't think of them as spin half anymore. The spontaneously trimerized singlet phase of spin-1 Kagome is essentially, in fact, is same as, it's just a large AF limit of the dimerized hexagonal singlet phase of the Hida model. And we believe that this family of organic salts actually realize dimerized hexagonal singlet phase, or you can call it equivalently TS, trimerized singlet phase at low temperatures. Thank you very much. Oh, I was perfectly in time. Yeah. I'm generally worried about my time.
Okay, questions, comments?
So I was just wondering, for example, the point in blue suggests that they are adiabatically connected, right?
Yeah, that is the point.
Right, but then you also say that it's a moment formation transition, so I'm kind of confused.
So yes, I will, so I'm saying here, for instance, in this part, the dimerization has happened. Now dimerization is there in all this region, including here, here, here. But after the moment formation transition happens, it smoothly, from a dimerized singlet phase, it smoothly turns into a TS phase. They are not two different phases in that sense. They are qualitatively the same phase, except that the binding is strong or weak. So from DHS to TS, it's just a smooth evolution. It's a qualitative change, it's the same physics basically. In fact, if you just one slide I may like to revisit. So if you look at, for instance, not these two. Yeah, so if you look at, let us say, the structure factor of the dimerized hexagonal singlet, what we call as dimerized hexagonal singlet, the trimerized singlet. So these two are calculation from the Hida model. And this is calculation from the spin-1, JF equal to infinity limit calculation. And they basically all look the same, except for the intensities and the sharpness of contours may change here and there. But they are actually same. Whereas it is different for the hexagonal singlet phase. So DHS is same as TS. Yeah.
Further questions?
Yeah. Oh, okay.
Oh yeah, just one more.
In the OD plot also there is a small kink.
In the let me see. Yes, there is one. That is true, but I don't quite understand that. Yes. In fact, remember, these quantities are the so-called more direct physical measurables in some way. But remember, the mean field theory has these internal parameters. They also exhibit some kind of, but so I don't quite, it's not immediately, yeah, I will reserve my answer because there is something else happening, but I don't quite understand that. But the most interesting aspect from the discussion that I am trying to project is that there is a moment formation transition, independently there is a dimerization transition.
All right, if there are no further questions, let's thank Brijesh again. And we break for lunch now.